Okay, so in this problem, we have the motion of a pendulum oscillation between the times of 0.5 and 2.5 seconds in a graph. Identify the period and amplitude by drawing and labeling on the graph's picture, and write the numerical values of the period, amplitude, and frequency. So here we have time that is graphed against displacement, and we can see that the equilibrium point is when your time is equal to 0. And that is going to be at x is equal to 0, and we're going to call this the center of oscillation. After this, we have to find the amplitude. That is going to be the distance from the max to the midline. So your amplitude is going to be 3, have a magnitude of 3. And we can see that is also the same when you're going down. That is also your amplitude. So amplitude is equal to 3.0 meters. Now let's compare from trough to trough. So when you are at a trough, one minimum, it occurs at around t is equal to 0.75, and then our next trough is going to approach at t is equal to 1.75 seconds. So you take the difference of those points, 1.75 minus 0.75, that is equal to 1 second, and you can also see that on the graph. So this is going to be your t. After this, what we have to do is label on the graph, which we already did. So these are our numerical value for our two components. Now for this, we have to find our frequency. So our frequency is equal to the number of cycles per second. So that is going to be 1 over t. Here that is 1 over 1.00 s, which is equal to 1.0 hertz. Now, let's move on to our second question. There's a 50 centimeter long pendulum with a 50-gram bob. What is the period of the pendulum on Earth in seconds? So here we're given that our length is 50 centimeters, and we're given that our mass is equal to 50.0 grams. Now, with the pendulum formulas, you need it to be in SI units, not in these units. So for 50 grams, we can convert this into a conversion factor. So that's going to be 0.0500 kilograms. And the length is going to equal to times your factor in centimeters, and then meters, grams, and then kilograms. So in 1 kilogram, there are how many grams? There's 1,000 grams. And then in 1 meter, how many centimeters are there? There's 100. So this is equal to 0.50 meters. After this, we don't know mass, but we'll see later that it doesn't affect period. So for a simple pendulum with small angles, that's equal to 2 pi times the root of L over G. In this, T is your period, L is your length, G is gravitational field strength. And if you're on Earth, that's just 9.8. Now, after this, the reason why we use this pendulum formula is because it swings back and forth. And if it swings back and forth, that is the reason why we have that trigonometric curve that is a sinusoidal wave. So why does it move back and forth? That's because we have a restoring force. And a restoring force is always going to bring it back towards the equilibrium. Now, for small angles, it is going to behave like simple harmonic motion for our pendulum motion. So the things that are not dependent on, that do not contribute to period, or aka things that our pendulum motion is not affected by, is going to be amplitude for small angles as well. Now let's get the pendulum period formula. How do we get T is equal to 2 pi L over root of L over G? So torque is equal to negative mgl sine of theta. That's because torque is equal to Rf and the perpendicular component, but here R is equal to L, and your tangential component of velocity is going to be mg sine of theta, because our pendulum is going to be, if you break down the components of mg, that's just what you're going to get, a negative mgl sine theta. So here, what you can do is you can say what your new, oh, this was L. So let's sub in our, instead of our R, we have our L. We have mg sine theta, so that's going to equal to negative mg L sine theta. Now we can use rotational Newton's second law. So our torque is equal to I alpha. Now for the pendulum bob, we're going to treat it as a point mass. And we're going to write out what the equation for that inertia of rotational inertia, which measures the resistance to torque for the object. So that's going to be I is equal to mr squared. But here that's I is equal to ml squared because R is equal to L. So also alpha is equal to d squared theta d squared. So this is going to be negative mgl sine of theta is equal to ml squared d squared theta over dt squared. Now if you simplify by dividing both sides by ml, this is going to equal to negative g sine of theta, which is equal to L d squared theta over dt squared. D squared theta over dt squared is equal to negative g over L sine of theta. Now sine of theta is going to be approximately equal to theta. So by using this in this step, you can simplify this solution. So you're going to get d squared theta over dt squared plus g theta over L is equal to 0, which is going to be reminiscent of d squared x over dt squared plus omega squared x equals to 0. So you can see that here, omega squared is going to equal to g over L. So if you take the root of both sides, you're going to get that omega is equal to the root of GL. So now after this, you need to convert the angular frequency to period. So for simple harmonic motion, you have that T is equal to 2 pi over omega. So if you substitute in how omega is equal to the root of g over L like we just found, then you have T is equal to 2 pi over the root of g over L. Now, if you take this and you want to move this fraction to the reciprocal, you're going to have to flip what is inside of the root symbol, and you're going to take the reciprocal of that. So that's going to be equal to 2 pi, which remains in the numerator, over L over G. Now, if you just substitute in your values, you have 2 pi. And here we were given that 50 centimeters, and here we have that, what would the period be if you jump to the moon? So if you have to examine the gravity on the moon, that's going to be given as 1.625 meters per second squared. So that's going to be 2 pi times the root of the length, which was 0.5 meters. And that's going to be divided by what our gravitational constant was, which is 1.625, which is equal to 3.5 seconds. After this, we are asked in 2C, how would the period if a change of the amplitude was increased? So the answer is that the period would stay the same. This is because in the formula T is equal to 2 pi L over G, there is no amplitude involved. So that means that the period does not depend on amplitude as long as the motion stays in small angle range where simple harmonic motion is valid. So in order for simple harmonic motion to be valid, number one, you're going to need to have small angle motion, and you're gonna need to have the period does not affect the amplitude. So that's what the answer is going to be. Now what you can see is that for a pendulum, when you use small angle approximation, the torque is just going to be proportional to negative theta. And what that means is that if you have a larger amplitude, that means that the object moves faster. The object moves farther, but it also moves faster because it's being converted to a different form. So those effects balance. So the period remains unchanged. If you have a very large angle, then sine theta is no longer a good approximation because the period becomes slightly longer. So, large theta, then when you use the sine function theta, is no longer going to be a good approximation because period becomes slightly larger or longer. So that's why we assume that there's going to be no change in period. No change in period because it's not dependent on it. Now, let's say that we had our next question. So how would this period change if the mass of the bob had doubled? Justify why this happens using physics concepts from prior units. Well, if the mass doubles, the period is still going to stay the same for the same reason that the last one stays the same. That's because T is equal to 2 pi times the root of L over G. So there's no mass. Therefore, if you double the mass, it's not going to change the period. And we can see that here when you write torque is equal to negative m GL sine theta, and I is equal to ML squared. So you're going to have negative MGL sine of theta is equal to ML squared alpha. If you cancel the m's, that's where you see the m goes away. So you have negative G sine of theta is equal to L times alpha. So what that means is that a heavy bob, or you say a heavier bob, that means you have more FG pulling it back, because in order to stay in the same position, you're going to have a larger force of gravity, because the gravity force is determined on a mass times the gravity. So mass is involved with the amount of gravity that needs to be exerted in order to keep the mass from not being up. From not being down and instead being up. Because naturally the gravity force is pushing it to the center of the earth, to the surface. Basically, now let's do our next question. A block of mass m oscillates on a frictionless horizontal table connected to an ideal mass of force constant K. The period of its oscillation is t. At the moment when the block is at position x is equal to 1/2 a and moving to the right, a ball of clay of mass m is dropped from above and it lands on the block. So what are we given? We're given the block's mass, we're given the spring constant K, we're given A, the amplitude of oscillation, and where the clay is going to stick is going to be here. So at this clay stick position, its x is equal to a over 2. So that means your block is moving right. Is going to be moving to the right direction. That's because the clay is going to be a mass of m. So when it sticks together, this means that we can declare that we have an inelastic, that is perfect, a perfectly inelastic collision. So now let's write down some of our. So again, we know that the block is moving to the right. The mass of the clay is m. This is a perfectly inelastic collision. What is the velocity of the block just before the clay hits? So we need to use some equations. Again, we are talking about E equals 1/2 k. Amplitude squared, k is equal to 1/2 kx squared plus 1/2 mv squared. Also, we need to use velocity, but specifically the simple harmonic motion form, which is v is equal to omega root of a squared minus x squared. Here, omega is equal to the root of k over m. And we need the period of a spring oscillator. So you can label this as t, and it's oscillating. That formula is equal to 2 pi times the root of m over k. Now, for the first question A, what is the velocity of the block just before the clay hits? You're going to use energy conservation. That's because the system is frictionless and there is no external work. So from that, you can conclude that mechanical energy is conserved. Same thing. Mechanical energy is energy. So what we first have to do is we have to write the total energy at the maximum displacement. So at the maximum displacement, you're going to be at the turning point. And this turning point is going to be at your amplitude. X is equal to A. So you would say you're at E, your E is equal to 1/2 KA squared. So at this point, here, all your energy is going to be spring potential energy. So that is going to be US. So now you have to write what your energy is at position X. So this was energy at max displacement, energy, max displacement, and next to it or below it, we'll write the energy at position X. So at any position, you will have that E is equal to 1/2 kx squared plus 1/2 mv squared. So here, your potential energy plus your kinetic energy is going to be your mechanical energy. So now all you have to do is use energy conservation, which we were just talking about, where E initial is equal to your E final. So you say that 1/2 kx or ka squared is equal to 1/2 kx squared plus 1/2 mv squared. Now all you have to do is you solve for the velocity that you were asked for in the question. So you're literally just going to multiply both sides by 2, and you're going to get that ka squared is equal to kx squared plus mv squared. Mv squared is equal to k. So you have to, or let's just show, we're going to subtract kx squared from both sides. So you're going to have ka squared minus kx squared. So what we see here is they both have a k. Therefore, you can factor out that k, and you have mv squared is equal to k a squared minus x squared. So then after this, what you have is you need to solve for velocity, right? So you're going to divide both sides by m, like this, and then you're going to be left with an m up there. But actually, I'll make this an uppercase m so that it matches. And then this side you divide by m. So after this, you have that v squared is equal to k times a squared minus x squared divided by m. And then you take the root of both sides, like that. And then v is equal to k over m, a squared minus x squared. So after this, you're going to sub in position. And what is your position? Well, we had our position up here. The clay ball is going to stick with the block at x is equal to a over 2. So that as a position, x is equal to a over 2, you are going to substitute that in for where you have a. So let's write that here. X is equal, or you're going to have that in where you have x. So that's x is equal to a over 2. So highlight this and then substitute that in there. So v is going to be equal to k over m a squared minus a squared over 4, because you squared it. So if you took this and you squared it, then that would be a squared, and then the 2 squared would be 4. So then you have here, this was v squared, by the way. V squared is equal to k over m 3a squared over 4. And that's because you can think of this as like 4 over 4, because that's the same thing as 4 over 4 is the same thing as 1. So then when you do 4 over 4 minus 1 over 4, that's equal to 3 over 4. So that's how you got k over m 3a squared over 4. So now you take the square root of both sides here. So v is equal to a over 3k over 4m. And that's your final answer for part A. Now, what is the velocity of the block just after the clay hits? So, just after, that's when your collision occurs. And that is going to be your perfectly inelastic collision. So during all collisions, you have the idea of conservation of momentum. So energy is not conserved here, but momentum is. So that's something that can occur. They don't always have to be hand in hand. So what you want is the initial momentum. So we're going to look at before your block. But then your clay is dropped vertically. Therefore, your P initial is equal to MV. And then your post-collision over here, you have that after collision, you're going to have M plus M due to the fact that it's no longer just two individual pieces of mass. You've now added them both together. So then we're going to say that post year is going to be VF. So then you're going to have PF is equal to M VF. P initial is equal to PF. And then you substitute in your A that you got earlier. Or your V, I mean. So this is just essentially this answer here. You substitute this in A. So then your VF is equal to and that's your answer. Now for our part C, what is the new period of oscillation of the block? So we know that post the clay sticking, so now you need the spring formula. Because we have a mass spring oscillator. So we know that here we have dependence on M and your spring constant K, because that's involved in the period. So what you need to do is write your new mass. So when you do these types of problems where you have where it's asking what is the new period of the oscillation, so you're literally just finding what the period is, and you're looking at things that are changing. So when you ask yourself, when this clay ball sticks to the new block, or to the block, what is the thing that changes? Your mass is going to change. Your K doesn't change because K is dependent on the type of material. But your M is obviously your mass, so you're going to have to account for the new mass. So your M old, or let's say your M new, is equal to your original mass plus your mass. So that's going to mean our TF, our final, or our new. So now you can divide, but we want to do this in a manner that we can express this in terms of the original period. So if you divide them, you're going to have that you have T scaled by M plus M over M or you have that TF is equal to 2 pi root of m plus m over k. Now you need to find your answer to part D. What is the new amplitude of the oscillations? Write your answer in terms of A, K, M, and M. Okay. So what you want is your new amplitude. So you have to look at post-collision. You have to first find your x, your position. So that's going to be x is equal to a over 2. And you also need to find what your velocity is. So that's going to be vf. And your new system is going to continue oscillating with your new mass. And this new mass was m plus m. So now you have to find your E total, and take note that this is simple harmonic motion. So you have 1/2 ka squared. So after this, you need to write your energy post-collision. Energy post-collision is your final energy. So your energy is going to consist of these two set equal to each other. So this is your E initial, and you need to find your EF. So E initial, EF, you're going to have 1/2 ka squared is equal to 1/2 ka over 2 squared plus 1/2 m plus m v squared. Now you sub in the velocity function. Again, that velocity was here. So this is going to be you're gonna have 1/2, you're gonna have VF from part B, that's gonna be m over m plus m, a over a times the root of 3k over 4m. Now all you have to do is you have to square it. So we're gonna square that, and we square that, so then that's gonna cancel out that, and you're gonna have to distribute that to the square to each of these. So we're gonna have squared here, and you're gonna have 4m, you're gonna have a squared as well. So now this is gonna look like this. VF squared is equal to m squared over m plus m squared times 3ka squared over 4m. So finally that's gonna look like this. VF squared is equal to 3ka squared m over 4m plus m squared. And after this, now you're just going to take this and you're going to substitute it into your energy equation. So now after this, what we had over here was your 1/2 ka squared is equal to 1/2 ka squared over 4 plus 1/2 m plus m. Let's rewrite that. So that's going to be m plus little m times your creation over here. So that was your VF squared, actually. So let's label that. So you're going to take that whole entire thing and you're going to substitute in this. Because this was earlier, this was just that VF, but not accounting for that square. So that's going to be squared 3ka squared m over 4m plus m squared. And after this, you're just going to simplify this. So here, your first term, you're going to have that this is equal to ka squared over 8, because you just multiply those together. And then for your second term, you're going to have to multiply all this through. So this is going to be 3ka squared m 8. So this is going to be over 8m plus m. And now you have to factor. So combinations to. So your final amplitude is going to equal to A over 2 root of 4m plus m plus m, because your 1/2 ka squared is equal to ka plus 8, and then this is going to be 1 plus 3m m plus m is equal to 1/2 ka af squared. So when you multiply both of these sides by 2, that's how you get rid of the 2 there in this side, and then you distribute that there, and then you're also going to have to take the root of both sides, and you also need to divide by 2, or you need to divide by k on both sides to isolate just a. So what I just deleted there was just a big M. And that is your A. So that's your answer. A over 2 for M. M plus, there's also another M here. You have your answer here of either of these. You had your V, which is this expression here, and you had your V, which is this expression there. So now let's do our very last question. So let's move this here. So you're going to have a block of mass M is attached to a horizontal spring with a spring constant K. The spring oscillates with amplitude A on a frictionless surface. So, because we know that it's frictionless, you can immediately see the buzzers being set off for the fact that mechanical energy is conserved. And mechanical energy is equal to your energy, which is K plus U, spring plus kinetic energy. After this, you're going to derive an expression for the total mechanical energy of the system in terms of K and A. So what you need to do is find when is your energy going to be the easiest to evaluate. So when is energy going to be easiest to evaluate? So because we know that mechanical energy is constant, therefore we know that we can evaluate it at any point. So what our easiest point is we're going to choose the turning point. And that's because at the turning point, that's when you have your max displacement. So at your turning point, that's when your x is equal to your amplitude. So, and also your velocity is equal to 0. So because kinetic energy is equal to 1/2 mv squared, if you multiplied 0 times that, it would just make it equal to 0. Therefore, your kinetic energy would also be equal to 0. So now let's find our spring potential energy. So we know that US is equal to 1/2 kx squared, the spring potential energy. So now we get that from integrating Hooke's law. So we know that Hooke's law states that F is equal to negative kx, but we want the work that is in the spring. So the work stored in the spring can be found by taking U is equal to the integral with the bounds of x and 0, so kx dx. So upon this, we are going to get U is equal to 1/2 kx squared. So now we evaluate that when x is equal to A. You can substitute that in. You're going to have US is equal to 1/2 KA squared. So then, because we know that velocity was equal to 0, right? So you can write that E is equal to U plus K, right? So then your kinetic energy is equal to 0. So that means your energy is equal to just 1/2 KA squared. So that is going to be your answer for this section. So that means that this is going to be the total energy of spring oscillator. Spring oscillator. So now after this, let's move on to our next part. So just derive the block passes. Okay, the block passes through EQM with a speed V max. Using the conservation of energy, you have to derive an expression for V max in terms of K, M, and A. So how are we gonna do this? So you can start off with the fact that at EQM, this is when the block moves fastest. At this point, because at x is equal to, because at equilibrium your x is equal to 0. That's because your displacement is equal to 0 because you're at your starting position. So that means that your spring potential energy is equal to 0. Now, if you use conservation of energy, you know that your E total, it's going to be constant. It's only going to convert from different forms. So you have E is equal to 1/2 KA squared. And at EQM, again, your U is equal to 0, as we saw here, which we'll highlight again. And all your energy is equal to K, is equal to kinetic energy. So now what is our kinetic energy? 1/2 mv squared. Therefore, at your EQM, your 1/2 mv squared max is equal to your 1/2 Ka squared. So you need to solve for your V max. So how do we get this? We can cancel out that 1/2 on both sides. So you have mv squared max is equal to Ka squared. Now after this, we can divide both sides by our m. And that cancels out. So your V squared max is equal to Ka squared over m. Now you simply just take the roots of both sides. So you have that V max is equal to A over K over M, because one of those A's, it cancels out and you can put it out there. So that's your answer for V max. For our next question, we have on the axes below, sketch the kinetic energy and the potential energy as functions of displacement from equilibrium. Clearly label and draw your amplitude and your displacement on the x-axis and your displacement x-axis. Okay, so let's just write down our key relationships. So U is equal to 1/2 kx squared So for this, U is equal to 1/2 kx squared. That's going to be a parabola up, and then your minimum is at x is equal to 0, and your maximum is going to be at x is equal to positive A, x is equal to negative A. Now for your kinetic energy, you're going to have also a parabola, but it's going to be opening downward. So your max is at x is equal to 0, x is equal to negative A is going to be a min, and x is equal to positive A is going to be a max, or not a max. Well, those are going to be your mins, but I mean your mins on your right and your left. So this can also be written as an equivalent form of 1/2 Ka squared minus x squared. Now, what are our labeled points? at EQMX is equal to 0, so U is equal to 0, so K is equal to 1/2 K A squared. Now at X is equal to plus or minus A, you have K is equal to 0, U is equal to 1/2 K A squared, and your E total is going to be constant. And what's that equal to? It's equal to 1/2 K A squared. And this is going to be a horizontal line on your graph. So now let's move on to our next part. The amplitude of the oscillation is doubled. How does the total mechanical energy change? And how does the maximum speed change? So if the amplitude is doubled, you're going to have your amplitude nu is equal to 2A. So how does your mechanical energy change? So that we know that E original was 1/2 K. So we can see that this is what it's going to be scaled by. This is the only difference, really, because you can see that that's the same, that's the same. So it's 4x larger. How does your maximum speed change, though? The student claims the energy is greatest when the car is moving the fastest. Is the student correct? Provide a physics-based explanation using conservation of energy. The student is wrong. Because so let's test this out. But everything, E will always sum up to the same amount. So it just shifts between.
In this video, we're going to be doing some simple harmonic motion practice problems. First, let's discuss what makes something simple harmonic motion. This is when you have a restoring force that is proportional to your displacement. So your F restoring is going to be proportional to negative x. This negative sign means that it is going to go back. That is the restoring component. Let's also talk about when the speed is the max. So you're going to have V max at equilibrium. And when is our acceleration going to be max? That is going to be at your maximum displacement. Also, what do we have that is going to determine our period? Our period is when our cycle starts again. We have cyclic motion when we have a restoring force and springs. So we have Fs is equal to negative kx. We're going to have our mass and our stiffness, which is k. from our spring. And if you're given a pendulum, it's going to be determined by the length, L, that you're given of the string, and also gravity, your gravitational constant, which is going to be 9.8 meters per second squared, not the amplitude. Let's quickly talk about the energy flow. At your displacement max, kinetic energy is equal to 0. Potential energy is max. Again, at your equilibrium, kinetic energy is going to be max. Potential energy is equal to 0. As we can see here, potential energy is greater when you're farther away from equilibrium because you have the potential energy to be stretched back or compress more. So from here, our energy constantly swaps from EQM to displacement, back and forth. Now let's solve some problems. Okay. So let's start here. A 0.65 kilogram particle in simple harmonic motion has an amplitude of 4.5 centimeters and a rotational velocity or angular velocity of 7.5 rad per second. So how can we do this? What you first need to know is your equation. We want to find the max velocity and the total energy. So we can start with the simple harmonic motion position equation. We have xt is equal to and using calculus, or you won't need to know this for AP Physics 1, but the derivative of v of t is going to be dx dt, and then that's going to give you v of t is equal to negative amplitude omega sine omega t plus angle. So in AP Physics 1, you know this from just looking at the graph, that when you have your cosine and sine, it's going to be shifted by a period. Or it's going to be shifted in its starting location. When you look at your graph. So yeah, when you have sine, it's like that. But when you have cosine, it's like that. Cosine x, and there's your sine x. So now what we have to do is we have to find the max value. We know that sine ranges from -1 to 1, and our maximum magnitude, which we're going to use to find our velocity, sine omega t plus your angle, yeah, that's just going to be 1, as you can see here. The absolute value of that is going to be 1. So your V max is equal to your amplitude times your omega. You're just going to substitute in your values. You had 0.045 and 7.5 rad per second. Make sure that this is in kilograms because you want it to be in your standard units. And this is going to give you 0.34 meters per second as your V max, which is going to be your answer for part A. So this is for part A. Find the total energy. So you need to use your energy formula directly. In simple harmonic motion, you have E is equal to 1/2 m omega squared A squared. And after this, we can square the terms and plug in. So here we have 1/2, 0.65, 56.25 times your A. So that's 0.045 squared. And that's going to give you 0.0370 joules. A 80 centimeter long pendulum, as measured from the pivot to the center of mass, is hanging vertically from the ceiling. The string is effectively massless. A student displaces it to the left 9 degrees from the vertical and lets it oscillate. The small angle approximation applies. So that's because our angle is 9 degrees and it's going to be under 15, so we can just assume that it's going to be small enough. So let's start with our force. For this, we have our pendulum and it's hanging from the ceiling. So upwards, we have your Ft. Downwards, you have your mg weight, Fg. So for the pendulum, the restoring force is the tangential component of gravity. I should say tangential. That's your restoring. So now you can use Newton's second law in your tangential direction. Your pendulum will always make this circular path. As you can see, it's like circular motion because that's the radius and the tension force is at the center. It would just spin around like that. And if that was a ceiling, obviously it wouldn't go above that, but if you had like your hand there and you were spinning it, it would be like a vertical circle. So your summation of your forces, MAT, F is equal to MA. And you can plug in your forces. You have negative mg sine theta down and MAT. You can cancel out the masses. You have g sine of theta. Now we can express our tangential acceleration. We have circular motion. So A of t is L squared. And this we can sub back in. And after this, we can divide both sides by L. After this, you have and since this is a small angle, so your equation is just going to be D. And we know that with simple harmonic motion, so here we can substitute that in. Now we can calculate our angular frequency, which was what our question was asking us to do. What period should this pendulum have? What would that make its frequency? How are frequency and period related? So omega here is the root of g over L, which we have written there. So in your calculator, we would plug in 9.8, 0.80, 3.50 rad per second. For period, you have 2 pi over omega. So that's 6.283, 2 pi. divided by 3.50. That's 1.80 seconds. Does the mass of the pendulum's bob affect how long it takes to swing back and forth? Why or why not? Oh, we need the frequency. So that's 1 over t. It's this the reciprocal. 1 over 1.80, that's 0.56 hertz. That's the units for frequency. And period is measured in seconds because it's time. So for the mass, in your equation, you have t is equal to 2 pi times the root of Lg, and it does not have mass in the equation to calculate. Therefore, mass does not affect period. Doesn't affect period. And now, okay. What would the amplitude of this swing be? Write a motion equation for its x position versus time graph using the original displacement and assuming it never decays. No friction, drag. So you need to first convert your angle into radians. So our angle was 9 degrees. So you're going to take 9, and it's in degrees right now. Degrees is massless, so pi over 180 degrees. So that would be 0.157 radians. Now, after this, you need to get the linear amplitude. And you can get that by looking at the arc amplitude. You look at the arc. Your arc is equal to L, length of your string, times the angle. So here that's 0.80 times 0.157. That's 0.126 meters. Approximately 0.13 meters if we're looking at sig figs. Draw out the position versus time graph. Put numbers on the axes for the equation showing at least 2 full cycles. Okay, so what you have here is that your pendulum is released from rest. Released from rest. If it's released from rest, at the max displacement left, that means that our initial position is going to be negative. So we know that so you have your equation x of t is equal to negative 0.126 cosine 3.50 t. So for our position time graph values, we have our A is equal to a positive or minus 0.126 meters, and your period is 1.80 seconds. 2 periods is 3.60 seconds. So now we have our table of values that we can use, and we'll just draw the function graph here. So let's label these T1, T5, T7, T8. So your values are going to range from different times and different x's. So again, we can draw this, but with our times. So for our first time, we have a time of 0. For our next time, we have a time of 0.190. Then we have 1.80, 2.70, 3.60 to make this nice and even. So that's our t and that's our 2t. So for your x, it's going to be measured in meters and your t is measured in seconds. So you start off at 0 and then you go to negative 0.126. Negative 126, and you go up to positive 0.126 seconds. Your first value is going to be negative. Then you go to 0. Then you're positive. Then you're 0. And then you're negative again. So that curve would look like this. And we can see this is correct with our graph because it's a negative cosine graph. Cosine x is usually like this. So if you have a negative cosine x, that is going to be a vertical reflection, and it would look like that, which matches with what we have. Now we want the velocity function. So for our last question, we know v of t is equal to dx over dt. We know that velocity, what we just plug in, so v of t is equal to 0.126, 3.50 sine 3.50 t. That's 0.44 sine 3.50 t in meters per second because this is velocity. Now let's move on to our next question. When a 75 kilogram person gets into a 1,200 kilogram car, the car springs compress vertically by an additional 0.6 centimeters. So we're asked, what is the spring constant of the system? And ignoring damping, what will the period and the frequency be of the vibration when the car hits a bump? These are reciprocals. So let's write down what we were given. We have the mass of the person, 75 kilograms, mass of the car, 1,200 kilograms, x is equal to 0.6 centimeters. Now converting that to meters, that would be 0.0060 meters, and g is 9.8 meters per second squared. So we need to find the spring constant, and you have to understand what is going to cause this compression. It's caused by the additional weight of the person. Additional weight of the person. So that means that if it's compressed to this amount, we can say that it's in a new state of equilibrium. So that means that it's going to be at a new static equilibrium, which we can say summation of forces 4 is equal to 0. So we can say that spring force of the car is now equal to the new weight of the person, Fw. So now we can write our forces. Fw is equal to Fg, which is equal to mg. So let's set those equal and continue solving. Yeah, so continue doing this over here. Kx, Fs is equal to Kx and our mg. We want the spring constant K, so you're going to divide by x. And you're going to get K is equal to mg over x. So you just substitute in your values, 735 over 0.0060. That's equal to 122,500 newtons per meter. And that's equal to 1.2 times 10 power 5 newtons per meter with 2 sig figs. For your next question, we have ignoring damping. What will the period and frequency of vibration be? Okay, so the car hits a bump. So we're seeing now that the person is in the car. We see that the car and the person, they're gonna oscillate together. Oscillate together. So you have to find the mass of this new thing. So your total mass of your system is 1,200 kilograms plus 75 kilograms. That's the car and the person. So 1,275 kilograms. Now we'll use mass spring period. So we have that period is equal to 2 pi m over k. That's just 1,275 over 1.225 times 10 to the power of 5. And that's equal to 0.64 seconds. So for frequency, that's equal to 1 over t. And that's equal to 1 over 0.64, which is 1.56 hertz. Okay. Let's also consider whether gravity will affect this. So I want to ask, if you have gravity and this was on the moon, would your oscillation frequency be different? Well, no. And that's because, like, again, whenever you're asked one of these questions, you just look at the equation And if it asks, does something affect the thing that you're concerned with? Like, you just see that it's not in the equation. So omega is equal to k over m. There's no g, so it doesn't affect it. A 0.8 kilogram mass is attached to a spring with a spring constant 200 newtons per meter. It is pulled 5 centimeters from the equilibrium and is released from rest. So initially, it's at this spring situation, and then it's pulled 5 centimeters. So that's its natural. And its mass is 0.8 kilograms. Let me just write that. We want omega. So we want period. .398 seconds. We want maximum velocity. So that's amplitude times omega. Our amplitude, 5 centimeters. And then it's 5 centimeters appears to be our max. So we're going to use 5 centimeters here. So that would be its maximum compression and our stretch. So that's our amplitude. That would be 15.8 omega, which we calculated 0.79 meters per second. Now we want our total energy. We're only going to have spring energy here. $200. And that's our solution. Now, next question. A 0.75 pendulum is displaced 8 degrees and is released from rest. Derive the expression for the angular frequency and calculate its value. So, our length is 0.75 meters. Our angle is 8 degrees. So, like we did before, we have our tangential force. We want this in simple harmonic motion form. We know that this is equal to negative omega squared x, our relationship here. So we'll just have that. And what we need is to divide by L. Or no. Take the root and divide by x. 3.62 rad per second. When a 70 kilogram person gets into a car, the spring compresses an additional 0.005 meters. Find the spring constant. Well, actually, first, I realized I did not finish this question. So that was the answer for A. For B, it's going to equal to 1.73 seconds. Now, you want your linear displacement. Linear displacement is going to be our linear amplitude, because that is the max displacement. So those will be when your graph is going to be at its peaks. We had to first convert our angle into radians because we were given it in degrees. And we use our conversion factor of pi is equal to 180 degrees to cancel out degrees. We get 0.140 rad. Now we have x is equal to L theta. Like we did before, we're going to try to get the sector. And you're going to multiply that by 0.140, and that is going to equal to 0.105 meters. So now we're asked, does mass affect the period? So let's look again at our equation. T is equal to 2 pi root of L over G. There's no mass in this period. So the answer is no. Mass does not affect period, just like we saw before. A 70 kilogram person gets into a car. The spring, when a 70 kilogram person gets into a car, the springs compress an additional 0.005 meters. So mass of the person is 70 kilograms. X is equal to 0.005 meters. We need to get our spring constant. So knowing that F is equal to mg and Kx is equal to Fs, here we know that they're going to be equal to each other. So Fs is equal to Fg, Kx is equal to mg, K is equal to 686 over 0.005, and K is equal to 137,200 newtons per meter. Now we need to find the period of the oscillation period when it hits a bump, and the mass is 1,200 kilograms. So for part B, you need to find the total mass like we did earlier. So that's 1,200 plus 70, 1,270 kilograms. T is 2 pi root of m over k. T is, now we're going to have 2 pi m was 1,270 over 1,37200. Now T is equal to 0.604 seconds. Our last question, does gravity affect the oscillation frequency? Again, like we've seen before in the other question, omega is equal to k over m here. There is no g, so it does not affect, because it's not in the equation.